Good morning, dear students. So, in the last class, we have discussed so many concepts, and I had informed you in the group that I will discuss the derivation once again because it was not visible to you people and students. It's quite difficult because since it is online class, the board was not big with me, so that it was difficult to me. So that I have found this way. Let me go through the derivation once again. So the chapter name is electric charges and fields. So let us see the derivation once again. I think you can see here I'm going to highlight force between multiple charges. So superposition principle I have discussed, and we are applying that superposition principle to the force to the multiple charges. So what does the superposition principle states here? When a number of charges are interacting, the total force on given charge is the vector sum of individual forces exerted on the given charge by all other charges. So here I think you may find it difficult while reading the sentences, but the thing is that the resultant force will be equal to the sum of the forces acting because of the other charges. The resultant force whatever we are getting will be equal to the force we are getting through the other point charges, and we are going to do the sum of that vector sum of that will be equal to the resultant force F what we get. That is all is the point. Since I have told you in the last class, I'm not going to repeat once again now the definition. So we are going to apply it to find to find the force between the multiple charges. You can see here the this one diagram. So we have taken the point charges, many charges, multiple charges Q1 here. You can see Q2. I'll highlight Q2. Here it is Q3. So here the force acting on Q1 is F12. So here what is the 1-2 denotes? It is the force acting on the charge Q1 due to the charge Q2. That itself the F12 denotes. I'll repeat once again. Here F12 denotes the force acting on the charge Q1 due to the charge Q2. So here the Q1 force is F1 here, you can see that. And here the distance between the charges are denoted by R12 here. The distance between the Q1 and Q2 charges R12. The cap represents the unit vector, you already know that. And here the distance between the charge Q1 and Q3 is R13. So you can see here easily. So go through the diagram, you will get to know. So let us apply. Here I am considering the system of the three charges Q1, Q2 and Q3 as shown in the figure. I have considered the three charges Q1, Q2 and Q3. So let us see now what is the force acting on the Q1 due to the Q2. We are going to find out the force which is acting on Q1 due to the charge Q2. We are calculating the force acting on the charge Q1 due to the charge Q2. So that we are taking it as a F12. I already told you what does the F12 denotes here. The force on the charge Q1 due to Q2. So that is equals to we are applying here Coulomb's law. Well, according to that, you already know the formula. So based on that, we are applying here 1 over 4 pi epsilon naught Q1 Q2. That is the inversely proportional. The force is inversely proportional to the distance square. That is the statement of the Coulomb's law. So here R12 square and here R12 cap. So we are introducing the unit vector here, that is written as in the vector form. We have taken the Coulomb's law in the vector form and we are applying for the multiple charges. So that is all is the thing. So we have denoted this as the equation number 1. You can see here. So here where R12 is the distance between, here R12 is the distance between the charges Q1 and Q2 is R12. Here what does cap denotes? R12 cap is a unit vector in a direction Q2 to Q1. So now we are calculating, we have calculated here the force on Q1 due to Q2. Now we are calculating the force on Q1 due to Q3. So how do we write using the Coulomb's law? Again, you can see here I am highlighting F13 is equals to, here F13 means the force acting on the charge Q1 due to the charge Q3. So F13 is equal with the vector symbol is equal to 1 divided by 4 pi epsilon naught Q1 Q2 R13 square R13 cap. here. Cap denotes the unit vector. Unit vector is the one which has the single magnitude. So that we have taken as the equation number 2. Here where R13 is the distance between Q1 and Q3, and R13 cap is the unit vector in a direction Q3 to Q1. The cap shows the direction, vector itself is which has the magnitude and the direction. So now we are going to calculate the net force on Q1 due to Q2 and Q3. We are going to calculate the net force acting on the charge Q1 due to the charges Q2 and Q3. So by parallelogram law, we are taking parallelogram law here. So we can write the equation as F1 is equals to F12 plus F13. So we have calculated here. See the equation number 1 and 2. We are adding that. That's all, because the vector sum only gives the resultant force. F1 is equals to F1 to F13. What is the F12 here? See the equation number 1 and equation number 2. So take out the common factor, whatever you find here. Take out 1 over 4 pi epsilon naught outside since it is common. So Q1, Q2 divided by R1 square plus Q1, Q3 divided by R13 square, R13 cap. So we have just here taken the equation number 1 and 2 and we are adding and we are taking vector sum. So here net force on Q1 due to all other charges is given by the superposition principle as see here. So what I have done here is like we have added F12, F13, so on. So I have added here, see the equation last class also I have explained you. So 1 over 4 pi epsilon naught with the bracket Q1, Q2, R12 square, R12 cap plus Q1, Q3. So the forces on the charges we have calculated. So since Q1 is common in all the terms here, see Q1 and Q1 here. So we can take it out, right? So 1 over 4 pi epsilon naught already we have taken out since it is a common. So Q1 also we have taken. We have written Q1 divided by 4 pi epsilon naught. So we are doing here summation. So sum we are doing, we have taken summation I is equals to 2 to n can be written as, generally we can write instead of writing Q2, Q3, Q1. So here I ranges from, already Q1 is there. So I starts from 2 to n values, 2 to n values. So I is equals to 2, 3, 4, 5 up to n values. So we have written the range I is equals to 2 to n. Qi, we have instead of writing Q2, Q3 here, so we have taken Qi as the generalized form. So R1 I square. So instead of writing 2, 3, 4, we have taken I here, R1 I cap. So this is the final expression. I think you have got now what I said here. I have just explained you only the mathematical steps as I have explained you in the last class, but you was unable to see the board properly. Okay. So now let me move further. So I have already discussed the last class also the limitations of Coulomb's law, dear students. Once again, I'm going through because I was not satisfied when I did the lesson. So Coulomb's law is applicable only for the point charges. Only for the point charges it is applied. It is applicable. I have already told you it is applicable. It is only applicable when the distance between the point charges is greater than 10 raised to minus 15 meter. So 10 raised to minus 15 meter. You can see here the second point. 10 raised to minus 15 meter is equals to 1 for me. So it is applicable when the distance between the charges, when the single charges, that is point charges means small charges, I can say. It can be applied only for the small charges. Coulomb's law can be applied. So this law is applicable when the 2 point charges have the distance between them as 10 raised to minus 15 meter, that is 1 for me. So let us go through what is the SI unit of the charge here. So SI unit of the charge is Coulomb. Coulomb is the unit of the charge. Its symbol is written as the capital letter C. So I think you have understood. So now, definition of Coulomb. How do we define Coulomb as? 1 Coulomb is the charge which repels another identical charge. So 1 Coulomb is the charge which repels another identical charge. So it will repel the identical charge. Why does it repel? Because 2 like charges always, obviously they will repel. So 1 Coulomb is the charge which is required to repel the another identical charge with the force of 9 into 10 raised to 9 Newton. Here this value is of 1 over 4 pi epsilon naught, which you found in the equation, that is 1 over 4 pi epsilon naught. So that value can be written as 9 into 10 raised to 9 Newton. So 1 coulomb is the charge required to repel the another same charge. So to repel that, we need the force of 9 into 10 raised to 9 Newton. So if we are repelling a charge with the force of 9, we are repelling a 1 coulomb charge. So I'll mention here, if we are going to repel a 1 coulomb of charge with another identical charge by applying the force of 9 into 10 raised to 9 Newton, then it is defined as 1 coulomb. I'm talking about 1 coulomb. So let us move on. So next concept I have taken here, continuous charge distribution. So continuous, what does mean by continuous charge distribution here? A system of closely spaced charges is called continuous charge distribution. A system of closely spaced charges. The charges are closely spaced. If at all the charges are closely spaced, that system itself is called as continuous charge distribution. There should be, the charges should be placed continuously closely spaced. So that kind of charge distribution is called as continuous charge distribution. So these are of three kinds. Here you can find out. These are of three kinds here. So first one is linear charge density, second one is surface charge density, and third one is volume charge density. So let us see what is linear charge density. What is the linear charge density here? So see, it is linear charge density is denoted by the symbol lambda. Here you can see in the bracket. So charge per unit length itself is the linear charge density. Unit length means, unit means 1. So the charge in a place of unit length, in the unit length, how many charges are present, that itself is called as the linear charge density. So if the charge Q is uniformly distributed over the line, assume that I have taken a line of length L here. If I have taken a line of length L, you can see the diagram here, how the charges or positive charges are placed here on the plane I'm taking here. The positive charges are placed here. If at all the charge Q is uniformly distributed over the line of length L, then the linear charge density can be written as lambda is equals to Q by L. So Q means the charge divided by the charges are placed per unit length. That is why you are writing divided here. Q divided by length, charges are placed per unit length. That itself is lambda. That is linear charge density. So its unit is, so you can easily, if you have studied in your PUC classes the chapter units and measurement properly, so you can easily write here. So see here, what is the unit of charge here? Coulomb, that is capital C you have written here, divided by length, it is the denominator, that is meter. When you take it to the numerator, it will become m to the power of -1, that is per centimeter. Per centimeter is the unit of linear charge density. So if the charge we are talking, if we have spoke till now about the uniform charge distribution. So if at all in the case the charge distribution is non-uniform, andre ಯೂನಿಫಾರ್ಮ್ ಆಗಿ ಈಕ್ವಲ್ ಆಗಿ ಸ್ಪೇಸ್ ಆಗಿಲ್ಲ, ಪಕ್ಕ ಸ್ಪೇಸ್ ಆಗಿಲ್ಲ, ನಾನ್ ಯೂನಿಫಾರ್ಮ್ ಆಗಿ ಎಲ್ಲೆಲ್ಲೋ ಸ್ಪೇಸ್ ಆಗಿದೆ ಅಂತಂದ್ರೆ ಲ್ಯಾಂಬ್ಡಾ ಇಸ್ ಈಕ್ವಲ್ಸ್ ಟು ಡಿ ಕ್ಯೂ ಬೈ ಡಿ ಎಲ್ ಅಂತ ಬರಿಬಹುದು. ಹೇಗೆ ಅಂದ್ರೆ, ವೇರ್ ಡಿ ಕ್ಯೂ ಇಸ್ ದ ಸ್ಮಾಲ್ ಚಾರ್ಜ್ ಯೂನಿಫಾರ್ಮ್ಲಿ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟೆಡ್ ಓವರ್ ದ ಲೆಂತ್, ಸ್ಮಾಲ್ ಲೆಂತ್ ಡಿ ಎಲ್. ಸೊ ದ ಟೋಟಲ್ ಚಾರ್ಜ್ ಆನ್ ದ ಲೈನ್ ಕೂಡ ನಾವು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಬಹುದು. ಹೇಗೆ? ಕ್ಯೂ ಇಸ್ ಈಕ್ವಲ್ಸ್ ಟು ಇಂಟಿಗ್ರೇಷನ್ ಯಾಕೆ ತಗೊಳ್ತೀವಿ? ಸಮ್ ಮಾಡಕ್ಕೆ. ಸೊ ಕ್ಯೂ ಇಸ್ ಈಕ್ವಲ್ಸ್ ಟು ಇಂಟಿಗ್ರೇಷನ್ ಆಫ್ ಲ್ಯಾಂಬ್ಡಾ ಆಫ್ ಆರ್ ಇಂಟು ಡಿ ಎಲ್. So we are showing the vector symbol here. We have to compulsory write it. So this is about the linear charge density. So let us go to the next concept, surface charge density. So surface charge density is denoted by the symbol here. You can see sigma. We call it as sigma, charge per unit area here. So per unit area, if per one area, for example, take unit means 1. So unit area means, for example, 1 meter square or 1 centimeter square. For your understanding, I'm telling. For example, if in an area of 1 meter square or 1 centimeter square, the charges are accommodated, the charges are arranged, then it is called as surface charge density, that is charge per unit area. In a unit area, how many charges are present? So that we are calling it as a surface charge density. If the charge Q is uniformly distributed over surface S, then we can write it as sigma equal to Q divided by S here. So here Q is the charge, S is the surface area here. Its unit is centimeter square here. Area we write it as a meter square. Okay, length into breadth. If charge distribution is non-uniform, then it is written as sigma is equals to dq by ds, where dq is the small charge uniformly distributed over the small area ds, then the total charge in surface. If you want to take the total, we have to take it integration, that is q is equals to integration of sigma of r into ds. ds is the small area. So if you see this diagram, you can understand this is ds is the small area. The charges are arranged over that. You can see here. We cannot say that charges are present in the x plane or y plane, z plane. For in our current example, it is charges are present in between the xy plane, you can say. So wherever we can take it as. So you can see here. So this is the small ds is the small surface, and around that the charges are present. Okay, let me not drag it. So third one is the volume density of the charge, that is denoted by again rho. We can say it as rho, charge per unit volume. So in a single unit volume, that is meter cube, we can say that. So in a single unit volume, how many charges are present? So that itself is called as volume density of the charge. If the charge Q is distributed uniformly over the volume V, then it can be written as sigma equal to Q divided by V. So some of the concepts I am telling you extra for your understanding, which is not there in your not there for your exams also. So that is the rho is equals to Q by V. Its unit is centimeter per cube. So you can see here in the diagram. So this is the volume dV. Around it, the charges are present. So I think you have understood this much. Any doubts, you can contact me in the group, dear students. So I'm going to stop at this point. Now, I'm going to stop at this point. Yeah, we have discussed, so far we have discussed the derivation and also the continuous charge distribution, the three types. That is linear charge density, surface charge density, and also the volume density of the charge. So we are going to continue the rest of the things in the next class, dear students. Thank you.